Hello, everyone. Welcome to the webinar. We will begin in a few minutes. Thank you for joining us today. If you have not done so already, please take a moment to respond to the poll on your screen. How many individuals are attending this webinar at your location? If there are more than 5 attendees present please type the number of attendees present in the questions box. Thank you. We will begin in a few minutes. Hello, everyone. Welcome to EPA's 17th Annual Drinking Water Workshop. We are glad that you could virtually join us here today for webinar session 7B on the source and treatment track on managing contaminants. If you have not done so already, please take a moment to respond to the poll on your screen. If there are more than 5 individuals in the room, please write the number of attendees present in the questions box. Thank you so much for those responses. Now I'll pass it over to Darren Lytle, who will introduce our first speaker and help moderate the webinar.
Hello, everyone. I'm Darren Lytle. I'm with the EPA in Cincinnati, Ohio. I work with a drinking water research group, and welcome to the 17th Annual Drinking Water Workshop. For many of you, this may be going on a third day here, and welcome back to those that have come back. Can't believe we're already into our last day, but we are, and this goes by so fast. But I want to thank you again for joining this session. Just as a reminder, this is session 7B. We're going to talk about source water and treatment, managing contaminants. Before we begin, I just want to make you familiar, if you haven't participated yet, on your webinar panel on the screen. We encourage you to ask questions for the speakers throughout the webinar by entering them into the questions box. So the way we're going to do this is we're going to have each speaker talk for about a half an hour, and then at the end there's going to be a half an hour of Q&A, which I will moderate. So make sure you get those questions in, and I can try to pass those along, and we'll have our speakers address them at the end. The presentations are going to be available in the handouts tab on the GoToWebinar control panel, as well as the link as a link sent to this question in the questions box. So and also the bios will be there as well. So I'm going to introduce the speakers, but the full bios will be in that tab as well, in that panel. Just as an FYI, the webinar is going to be recorded and will be available in a few weeks at the link provided in the questions box as well. So I think I covered everything. So with that said, let's get started with our first speaker. Our first speaker is Dr. Simone Triantafillidou. She is an environmental engineer at EPA's Office of Research and Development in Cincinnati. Her research interests include aquatic chemistry, corrosion science, drinking water quality and treatment, sustainable drinking water infrastructure, including premise plumbing and distribution systems, and public health. Simone earned her MS and PhD degrees in environmental engineering at Virginia Tech. I'm going to turn it over to Simone.
Thank you so much, Darren. I hope you can see me, hear me, and see my slides as well.
Yep, all looks good.
All right, perfect. So hello, everybody. I'm really excited to participate in another EPA Small Systems workshop. This has to be one of my favorite workshops to attend because I truly learn a lot. And this time around, I would like to discuss arsenic and co-occurring contaminants in tap water as well as treatment residuals. So I changed the title of my presentation a little bit compared to what is on the program. This is a presentation with Darren Lytle, who's moderating this session, although a lot of folks need to be acknowledged, and I'll do that later on. All right, so I'll take us back on memory lane here because even this very workshop really started with the US EPA's arsenic demo many, many years ago. And I'll just remind perhaps some of the newbies what that demo was even about, because we're going to be really delving into the data sets that came out of that have really a wealth of information that we could look at from many different angles. So the EPA a long time ago in 2001 announced the lowering of the arsenic drinking water maximum contaminant level to 10 parts per billion, or else 10 micrograms per liter. And at that point, there were a lot of small systems that would not be able to meet that threshold. So the EPA at the time announced a really big research and development plan to help small systems achieve the new MCL. And as part of the overall effort came the EPA's arsenic demonstration program specifically, which installed and evaluated a variety of arsenic removal systems at 50 small drinking water systems around the United States. This is an old program. It was completed in 2010. It started in around 2004, but we can still learn many things from it. Gratefully and thankfully, the EPA reports have been made publicly available to everybody for each of the 50 small system projects. And this is actually the website that I used myself to retrieve the reports and a lot of the data and information that I'll be talking about today. So just a great visual of where the 50 sites of the original arsenic demo were located around the United States. I'll be citing Tom Sorg a lot, who was one of the leaders of the arsenic demo, so you'll be seeing his name a lot in these slides. So these are the 50 sites in the 28 states from 2004 to 2010. And interestingly enough, when Tom Sorg went back to ask these systems how they were doing in 2017, 90% were still operational, which is pretty impressive. So if you know a little bit about me, I'm really interested in distribution system and flowing water interactions, more so than treatment per se, although I'm trying to expand to other areas. So then where does the arsenic demo fit? Well, thankfully, there's a lot of information that we can get from it. And what I've been looking into the last several years really has been this notion that pipe scales are reversible reservoirs for inorganics, including arsenic and many others, and radionuclides. So I borrowed this schematic from the Journal of the American Water Works Association just to illustrate how contaminants that are coming through a pipe may actually sorb, deposit onto the pipe through a variety of accumulation mechanisms, either sorption or co-precipitation or sedimentation. So basically the pipes then become sinks for the contaminants to stay, but at the same time, through the reverse mechanisms, when that equilibria are disturbed, there may be a possibility for those contaminants to be released back into the water through the inverse mechanisms like desorption or destabilization. We may even have transformation or hydraulic disturbances that, for example, release particulates into the water. So by looking at what has been coming in to the distribution system right here versus what has been coming out, we can actually infer what are the mechanisms that have been going on around here. So this is what we've been trying to do by revisiting the humongous data sets that were part of the original arsenic demo. So the first part of my talk really is going to be on water quality at the tap based on that information. If you remember from an earlier slide, I talked about 50 systems overall that participated, but for the needs of this work, we focused on 20 systems only, because from the moment those systems installed arsenic treatment, they didn't have any known influence of other wells untreated for arsenic, or they didn't have any mixing of water sources that would affect water quality entering the distribution system and complicate our data comparison. So we just focused on the 20 systems for which we were pretty confident we knew what was the quality of the water coming in. If you look at my schematic at the bottom of the slide here, what's really amazing about the data sets is that we actually had information on arsenic, iron, and manganese available for the treated source well water, meaning the water coming into the distribution system, versus 3 home taps. These were actually per system. So these were homes, residences that were part of the Lead-Copper-Rule sampling pool in those locations, and they were sampled before and after arsenic treatment, following the Lead-Copper-Rule protocol, meaning a first draw water sample was collected 1 liter after a minimum overnight stagnation of about 6 hours, and that information really reflects the water that was coming out of the system at 3 different points of use per system. So this would be the water coming out in my schematic here at the bottom. What's interesting too is that we didn't just have screenshots of information that were collected once. There were temporal data for many months before and after arsenic treatment was implemented. That depended on the specific system. So there was, at least we could see trends through time. We weren't just relying on one data point, which makes the data more valuable. We did have some information available in the reports on plumbing materials for each system, for water mains, service lines, and premise plumbing, which could somewhat aid in data interpretation, although that information was not always available and for all systems, and we'll talk about that later on. So the first goal in revisiting this amazing wealth of information from the arsenic demo was really to assess arsenic release from distribution pipes back into water at the tap by having the amazing luxury of having arsenic, iron, and manganese levels, concentrations in water samples collected at the tap. This is not something we usually collect, right? Because these are contaminants like arsenic. Regulation requires collecting samples at the point of entry to the distribution system. So unless you have a water quality complaint or a discoloration issue, and then that gets investigated further, we just don't get to have that much information about what's happening at the top, and let alone through time and a variety of systems that we could compare. So really, it was a wealth of information that we absolutely had to take advantage of. This is a summary. I hope you can see my next slide. I don't know if there's a delay, but this is a summary of the systems that we looked into, the 20 that I mentioned. just to illustrate that we had different systems in different states, and that's shown on the first column right there. The second column is the arsenic removal technology that was used. So you'll notice that I grouped the 20 systems depending on what arsenic treatment technology was used. For example, I put the systems that used adsorptive media first, and then I moved on to other treatments like coagulation, filtration, and then you'll see in the next slide the remaining treatments. The water samples that we had available to us, it's this column here. So you'll see that we had monthly samples before arsenic treatment. So that's kind of a good baseline information. And then monthly samples after arsenic treatment. So if we focus on this kind of highlighted system here, GF in New Hampshire, you'll see that there were 4 data points for before treatment, and then 15 to 16 after treatment, depending on the distribution system site. So this is more than a year of data after arsenic treatment. It's pretty good information. The plumbing material information wasn't always complete. For this specific system, you'll see here what was reported in the EPA report, which is basically that the distribution system had PVC and the service lines and premises were made out of copper. I have highlighted another system at the bottom. I basically bolded it. This is a coagulation filtration engineering modification system. This is going to be an illustrative example later on when I'm showing you the data. That's why I've bolded this out. And unfortunately, we didn't have information on plumbing here. But this can give you a general idea of what kinds of systems we're talking about and what sort of information we had available to us. This next slide right here is the continuation of the 20 systems. I split them up into 2 slides because there was a lot of information to share. So you can see that as we're moving down the systems, we have iron removal systems grouped down here, and another one bolded because I'll be talking about this specifically as well. It had about the same amount of information for before and after treatment as the previous systems, and a bit of information here on the distribution system materials, which were PVC, but unfortunately not information on the service line and premise plumbing materials. So we looked into this data a while ago, and we identified 3 patterns of arsenic release into tap water based on that data. We published this information in the AWWA Journal of Water Science. And if anyone would like to have more detailed information compared to the highlights that I'm going to be presenting here, please feel free to reach out if you would like to get a copy of this manuscript. So here I'm just going to give you some high-level highlights. So let's go into the patterns. The way I've organized them is from simpler to more complicated. So let's start with arsenic pattern A, which was the simplest out of the 3. This pattern was observed in 6 out of the 20 systems that we looked into from the old arsenic demo. And the kind of information I'm presenting on this slide is going to be the same for the other examples for the other patterns. So let's look at the graph first. We have time from treatment in days. So time 0 is really where arsenic treatment started. Negative days to the left of that are just the period before treatment. And then to the right, you have the time from treatment. In this specific system is more than 400 days, which is really good information. And on the y-axis, we have arsenic concentrations. This is total arsenic in water in micrograms per liter, or else in parts per billion. What we want to be comparing in all of these graphs is basically the black data points, which is arsenic in water after arsenic treatment. So this is the water that was coming into the distribution system. This is the water in, versus the 3 colored curves and data points, which are the distribution side 1, 2, and 3. These are actually the home taps from the LCR sampling pool. These are the locations at the point of use, so the out that I was talking about. We want to be comparing in to out. So I've also summarized the data in the table on the right, where you can see averages and standard deviations per sampling site before and after arsenic treatment. So let's start looking at the data here a little bit. If you see, let's start with the black dots first. If you look at those, the arsenic treatment was working fairly well. There was really low arsenic when arsenic treatment started. It was almost close to zero after the treatment. As time passed by, there was a bit of a breakthrough through the adsorptive media system, so arsenic concentrations increase. And again, these are the levels after arsenic treatment coming into the distribution system. If we compare that to the three colored curves, they're pretty much the same. There's only one exception, which is early on here in the beginning of the arsenic treatment, where there's a little bit of a lag phase for the benefits of arsenic treatment at the well to be realized in the sampling sites. There was possibly some initial like destabilization period for pipe scales there, where arsenic coming out from those home taps, was a little bit higher than what was coming into the system. But after that, we could say that the three homes, the three distribution system sampling sites pretty much mirrored what was coming in. The arsenic treated well water was below the MCL throughout, and so were the home taps. And again, as a reminder, the distribution system here was made out of PVC, whereas the service line and the premises were made out of copper. So this really is the best possible scenario we could have. It's the idealized case where arsenic concentrations coming out of the distribution system really mirror what's coming into the distribution system at the entry point, and they really reflect this idealized expectation of arsenic being what we call a conservative inorganic contaminant that does not react with the distribution system. It's the simplest, cleanest, quite honestly, best situation in terms of managing contaminants that we could possibly have, and 6 out of the 20 systems were observed to have this behavior for arsenic. Now we're moving on to a more complex system of pattern B. This is just to illustrate the pattern. It's one of out of the 8 systems that followed this general trend, where you can see here things get a little bit more tricky. So water after treatment did have arsenic levels that were close to the MCL, but not a little bit lower than the MCL. But 2 out of the 3 homes, those that are depicted by the red line and the green line, you can see here certainly had arsenic measured at concentrations that were far higher and above the MCL. So for example, for distribution system 1, this is one of the 3 homes which is depicted by the red. Arsenic concentrations after treatment throughout the arsenic demo, if we average them out during that timeline, were 16 ppb plus or minus 2, a little bit of variability there. Distribution site 2 had 12 ppb plus or minus 2, so that was consistently above the MCL as well. Now these are home tabs, so they don't comparisons to the MCL don't have any regulatory impact, and in fact none of what we did here was intended to inform or affect any regulation or anything like that, but we just wanted to see how contaminants actually behave from a science perspective and a research perspective. So this case here, at least for the 2 out of 3 homes that were sampled, does demonstrate a non-conservative behavior for arsenic. It basically suggests that there was slow release here of arsenic at levels higher than what was coming in, which is indicative of arsenic desorption from the pipes back into the water. Now, unfortunately, this is a system for which we didn't have plumbing material information, but just looking at the water arsenic data, certainly 2 out of 3 sites had concentrations at the tap that were higher than the health limit of 10. I'm not showing you any iron results for this pattern B because they were not as interesting. Now, of course, we know that iron has a high affinity for arsenic, and oftentimes we look at arsenic contamination alongside with iron and manganese. But so far for pattern A and pattern B, those were not as interesting. So I'm not going to be showing them to you. But let's move into arsenic pattern C, the last and perhaps most complex out of the 3 that we identified. This was observed in 6 out of the 20 systems that we looked into. And again, if you look at this graph here, well, first of all, you'll notice there's no table offered alongside it. That's because there were a lot of spikes. You can see those on the graph. So calculating averages and standard deviations is not as meaningful because we have those single aberrant data points that would just make statistics a little bit weird. So instead, we can just look at the data qualitatively from the graph, where I'm hoping what you can see is that if we focus on the black arrows first and kind of the after treatment data points here, there's definitely been inconsistent arsenic treatment of the well water because there is particulate breakthrough from the treatment system. Again, the black is what's coming into the distribution system, but there are also arsenic spikes and variability within the distribution system, and those are, you can see here in distribution side 1 and here for distribution side 1 and 2 and 3 actually. So some of these spikes are occurring together for all the sampled sites. Some of them are just individually observed for a single site, for example, like this one here. So there is high variability in this pattern C. There's certainly spikes. These could imply that there's kind of a more complex combination of release mechanisms for arsenic in systems that look like this. So in addition to perhaps a low level of desorption, that kind of consistent low background release, there certainly is particle destabilization, and hydraulics seem to be a part of what's happening here. Now here it's interesting to show you iron because there's definitely spikes of iron that coincide with the spikes in arsenic. So on the left we have total iron in water in micrograms per liter. I've plotted the secondary MCL so that we can see where we are relative to that. And you can certainly see that, again, the breakthrough from the treatment system here, these are the spikes that are black, but you can also see spikes in homes that were sampled, like this big red spike here before day 200 of treatment. On the right, we have total manganese concentrations and again, the secondary MCL for manganese plotted here. And there are spikes as well of manganese that you can see. Now, this is a treatment that actually added permanganate as part of their treatment. So of course, you know, there's an expectation that there's going to be some more manganese there, but there are still some spikes that actually coincide with some of the iron spikes and the arsenic spikes. Some of them are concurrent, and those imply particle detachment. This is a summary of the results, and again, way too much data to look into now, but I just wanted to focus on this right column here, which is the determination of arsenic pattern in systems, just to illustrate that for systems that were identified to be under pattern A, you'll see here that a lot of them were the ones that were using absorptive media as their treatment. And the first illustrative example that I showed you is actually this highlighted system here of pattern A. When we move to pattern B and then pattern C, which is going to be on the next slide, we're now moving to different kinds of treatment. So they could almost be grouped based on treatment system and arsenic release pattern at the same time. What I wanted to also point out here is that even if a system was fell under arsenic pattern A, which is really the best case scenario, right? There's no interaction with the piping, and what comes in equals what comes out. But even then, that doesn't mean that we didn't have high arsenic levels. So if we look at another system here, which I didn't show you in detail, but we can just look at the summary statistics here. And this is system BW. It's right here. You can see that we calculated the percent of samples exceeding the health threshold of 10 micrograms per liter. And for the 3 distribution sites in that particular system, DS1, DS2, and DS3, more often than not, they were actually higher than the threshold. So we can have systems under this pattern that we're actually seeing arsenic levels higher than the MCL at the sample taps. Again, the illustrative example of pattern B is highlighted here, but I'm also showing you other systems of pattern B and just their summary statistics. And this is the remainder of systems and the illustrative example of pattern C. As we're moving down to iron removal systems, you'll see that the patterns in general move to more complicated B and C situations of non-conservative contaminant behavior, although there are some exceptions like this pattern A here. So in summary, I tried to visualize the data in a way that's perhaps a little bit more simple to follow, and I'm going to look at the time here. If we look at the treatment effluent, which is what was coming in, again, after arsenic treatment, arsenic concentrations were lowered. Hopefully, if treatment was working well, to way below the MCL. But the three patterns A, B, and C really where either had a lag phase in the best case, which is pattern A, which after that lag phase did mirror the now low arsenic concentration coming in, but patterns B and C were more complicated with additional arsenic release from the distribution system. So if we visualize our control volume then, which is really the whole water distribution system, and we have water coming in, this is water at the entry point, versus water coming out. This was at the 3 homes of the lead and copper rule sampling pool. For pattern A, there wasn't really any interaction of the water with the pipe material, but for pipe B, there was this kind of slow release, which again is indicative of a chemical release mechanism. For example, it could be desorption. And pattern C is really the most complex of all, where we have, in addition to some possibly chemical release, that hydraulic release, meaning the solid destabilization. So overall, we did identify 3 different patterns of arsenic release in tap water from the arsenic demo systems, and contributing factors to each pattern were the source water arsenic and iron levels, which really dictated, the type of arsenic treatment that was chosen. There was some information we could get from pipe materials as well that helped with data interpretation. But the arsenic release patterns at consumer taps had increasing complexity. So we started with pattern A, which was really mostly conservative behavior in simpler systems that had low iron and manganese in the source well water and plastic pipe materials in the distribution system when that information was available. But we then moved on to patterns B and C with non-conservative release in more complex systems where there was high iron and manganese in the source well water. There were iron pipe materials, according to the reports, whenever we did have that information, and there were occasional arsenic treatment complications as well. So overall, in some complex systems, not in all, arsenic and some other legacy inorganics may linger long after they have been removed at their source. And that's really important to be aware of in order to manage our expectations, because it doesn't mean that from the point you install arsenic treatment, the next day everything is going to be great and there's going to be no increased arsenic release observed at home taps. So this is the first part of what we looked into when we revisited the arsenic demo. And the second part was looking at residuals from the arsenic demo, because there was a lot of information on that as well. And residuals management from the treatment itself was a major consideration in an early survey that had been conducted. Obviously, the quantity of residuals generated by a given treatment process is important. Their type, whether the liquids and or solids, and their quality is also important because that will affect disposal options as dictated by regulations, either federal, state, and or local regulations. And even 10 years later, when Tom Sorg went back to the systems, media disposal was among the problems that were reported. So here's just some schematics of some of the treatments that were used. Adsorptive media were used in a lot of the small systems, and those can be either in series or in parallel. Iron removal was used in many systems, and coagulation filtration as well. And these really result in different kinds of residuals. So I've summarized them all here, but I'm not going to go into too much detail because I think I'm running out of time. But basically, we may have solid residuals like the exhausted media, for example, in an adsorptive media system. But we also have backwash water. It's part of the process, which may have solids into it as well. And even in iron removal and coagulation filtration, where backwashing is also part of the process, we also get backwash water as a residual with possible solids. And there's all these different kinds of residuals disposal options that were available at the time of the arsenic demo. And this probably should be expanded now, but these are just some visuals of, for example, this is direct connection to, to a sanitary sewer line of backwash water. This is here flowing directly onto the ground, evaporative pond and a recycle tank. But the point is that really residuals complicate things, and it's something that costs money, especially if they're hazardous, and that needs to be looked into. I've been looking alongside a great team of other researchers into all 50 systems of the arsenic demo, for which there was information on the backwash water and solids, but also on the spent treatment media, for example, for adsorptive media systems. We're still in the process of analyzing this data, so I'm not going to go into too much detail, but here's an example of what arsenic levels look like in the backwash wastewater. So this is arsenic concentration split into the particulate fraction on the red versus the soluble fraction on the blue for the different systems grouped per treatment. So for example, here we have the first group on adsorptive media, iron removal, and so forth. So you can see from the concentrations here, we have pretty high particulate concentrations, and the blues are not even visible, meaning that soluble arsenic was really low, which is to be expected. The whole point of backwashing is just to remove particulates and fluff up the media. And if you look at iron in backwash wastewater, similarly, there was really high particulate concentration, but not as much soluble. But if we kind of focus on the soluble, you'll see that it appeared really low on the previous graph, but here it certainly can be above 10, for example, which may complicate things in terms of how it's handled. And these are at the bottom, the corresponding soluble iron concentrations. So we looked into wastewater. This is a slide of backwash solids, where you can see arsenic on the top and iron at the bottom. So now we've switched to different concentration units, micrograms per gram, because we're talking about solids. And again, you can see the grouping of systems and the concentrations that we've observed. We are in the process of looking into other elements to perhaps get some mechanistic insights on how the media work. So from just this very preliminary compilation, we found that soluble arsenic levels in the backwash were often greater than 10, especially for the adsorptive media systems. Obviously, particulate arsenic is of much greater concern, was higher in coagulation, filtration, and iron removal systems. But the whole point of this analysis overall is to try and figure out if we can get an idea very roughly of arsenic and co-occurring contaminant concentrations in residuals based on the case studies of the arsenic demo. And we're looking into silica and phosphorus, for example. Can we infer if there's been silica or phosphorus competition for sorption sites, for example, relative to arsenic from the backwash data? So we're working on it, and more information is to come. But overall, there's been a great wealth of information on the arsenic demo to advance our understanding of arsenic levels at the tap after treatment, which, as I mentioned before, is really unique to have that knowledge at the tap, which is at the point of use where exposure happens, and to hopefully improve our understanding of the characteristics of residuals with this ongoing effort. With that, I'd really like to thank the project team that revisited the arsenic demo data sets, went through the reports, and analyzed the data and synthesized data and draw the conclusions alongside me. Tom Sorg, Lily Wang, and Abraham Chen were part of the original arsenic demonstration program, and really this work wouldn't be possible without their input and contributions. And Christy Mullen, Catherine Webster, and Justin Lytle helped tremendously with cleaning up the data sets, retrieving the data sets from the reports, and just helping with that part of the study. So I'm extremely grateful to them. Justin has worked really hard this summer looking into the residuals, and Christy and Catherine were looking into the tap water results from the reports. None of this would have been possible without Battelle Memorial Institute, which was the contractor for the arsenic demo, and of course the water utilities that participated. With that, I also like to thank Cadmus for organizing this virtual now workshop with all the challenges that entails, and of course the EPA and ASDWA for collaborating to make it happen. And I'm gonna turn it to Darren. Thank you.
All right. Thank you, Simone. So we'll go ahead. We'll jump into our next speaker, who's going to speak on cyanotoxins. And again, remember, put your questions in the question box. Our next speaker is Katie Foreman. She is an environmental protection specialist with EPA's Groundwater and Drinking Water Group, Groundwater and Drinking Water Office. She serves as OGW-DW's lead on harmful algal blooms and cyanotoxin issues in drinking water. She has a bachelor's and master's degree in geography from the University of Iowa. I'm going to turn it over to Katie.
Thanks, Darren. And thank you, everyone, for joining this session. I'm really excited to be here with the other panelists and to be participating in this great workshop. It's one of my favorites as well. So I want to just start off by talking a little bit about what I'm going to be discussing today. You know, most of what this presentation is going to be is talking about what the support tools are for managing cyanotoxins in drinking water that we've developed here at EPA over the course of a couple years. But also looking at what are harmful algal blooms and what are the issues around drinking water, and also looking at the recent activities that we've done here at EPA to manage that. So many of you are probably very familiar with harmful algal blooms. Either you deal with them directly in your systems or you come across them in everyday life. They are naturally occurring. And when we are talking about harmful algal blooms in freshwater, we are typically talking about cyanobacteria. It's a very common freshwater harmful algal bloom. So from now on, when I'm talking about harmful algal blooms in this presentation, I'm going to be talking about cyanobacteria. And these can rapidly form in surface waters based on several factors: excess nutrients, slow-moving water, elevated temperature. Those sorts of and other kinds of attributes can lead to harmful algal blooms. And some species of cyanobacteria also produce toxins, which I'll be referring to as cyanotoxins. And given this, not only the toxins, but also the blooms themselves have significant impacts to many different factors, including the human health effects from the toxins themselves, as well as the ecosystem impacts from toxins, and also hypoxia that comes from that excess algal mass that comes through as part of that harmful algal bloom. And there are obvious drinking water and recreational water quality concerns and associated economic losses based on all those factors, and also additional things in and of themselves. So really focusing on the drinking water challenges. The drinking water quality issues are unique to harmful algal blooms. There are several of them. Taste and odor issues arise from many harmful algal blooms in source water. There are cyanobacteria as a source of many of the contributing factors for taste and odor compounds. And not only that, but also, as I mentioned before, the actual cyanotoxins. So these toxins have health effects. And particularly when we're looking at the cyanotoxins, microcystins, and cylindrous spermopsin, you're looking at health effects from gastroenteritis to liver and kidney damage. So some significant health effects from exposure to large elevated amounts of these toxins in drinking water. And then also there's this potential for development of disinfection byproducts. Now this is an interesting factor in that there are several ways that HABs can contribute in your source water to disinfection byproducts in finished water, from the HAB material themselves being a precursor to DBPs, as well as the approaches used to manage the HAB can lead to disinfection byproduct formation in the distribution system within your system. Obviously, there are ways to optimize both, but being aware of that and also managing for both is critical during harmful algal bloom in your source water. So obviously, this provides many issues to public water systems, which I'm sure many of you are familiar with: the increasing costs, the ability to try to figure out how to communicate with the public, and also figuring out when do I monitor, when do I treat, and how do I predict this from happening? How can I get ahead of this? And then also this great thought of how can I prevent it? What are the things that we can do? What are the cost-effective methods to actually reduce them in source waters themselves? So those are, a variety of the challenges. And I show this screen to highlight the pervasiveness of HABs within the country. You'll see in that lower left-hand map, it's a little dated, but the map I think is important to show that across the country we are seeing, this is just sort of recreational impacts and the public health advisories are related to that, but you see a lot of green on that map. We're seeing a lot of harmful algal blooms in source waters across the country. And, we've seen harmful algal blooms in source waters in every one of the states in the United States. So this is a national issue. But I want to highlight a couple of the seasons that I think many of you are familiar with in the last 5 years and sort of the main big events that have happened. Obviously, there are local events as well, but I just want to highlight a couple given the drinking water ramifications. So the Ohio River 2015 bloom was a 700-mile bloom that span across multiple states, impacting millions of people's source water. It didn't result in any drinking water advisories. However, I'll mention that everyone had to be proactive to try to be sure that that risk was managed. And in Florida, many of you are probably familiar, those who are in Florida, and also those of you who follow the yearly HAB that happens down there in several different parts of Florida. And also the Utah Lake HAB event in 2016 was significant for recreational issues. And these are, for Florida and Utah, those are mostly recreational impacts, but obviously drinking water, folks had to be on guard and being sure that they were managing the risks if they did have a bloom in their source water. Now, I want to mention a couple of the selected drinking water detects that we've seen in systems in the last couple of years. And I want to note that this doesn't include the unregulated contaminant monitoring rule data that's being currently collected, but this is just giving you a flavor of the kind of detects we've seen in finished water across the country in a number of years. And you'll see that some of them, they were just detects. They didn't result in a do not drink, or they weren't even above a level of concern. However, some of them did reach that point and resulted in an advisory, for instance, some events in New York and Oregon and Texas. So it really does speak to how this is a pervasive problem, but very unique to different areas, and also solutions need to be pretty unique to particular situations. So given this need for risk management across the country with the pervasiveness of harmful algal blooms in source waters, here at the Office of Water, we've developed several and done several different activities to try to put it at a forefront to figure out how to manage cyanotoxins across the country. And one of those is we developed a 2015 two health advisories for cylindrous thermopsin and microcystins. And we also released in tandem a recommendation document to help utilities think about how and states think about how to manage cyanotoxins in drinking water, how to implement those health advisories. And then we do have a strategic plan that we submitted to Congress in 2015 as well, and I'll talk about that in a little bit more detail. We're also, as I mentioned before, we are monitoring cyanotoxins as part of the fourth unregulated contaminant monitoring rule. Many of you might be monitoring your systems this year even. We're spanning from 2018 to 2020. And so at the end of this year, we will have a full data set for cyanotoxins for that unregulated contaminant monitoring rule. We've included cyanotoxins on several of the last rounds of CCL, the contaminant candidate list. And we also are additionally doing other sorts of activities, including developing tools over the past couple years. I'm going to be focusing a lot of that in my coming presentation here. And then I also want to note that we've been doing other sorts of work that a lot of partnership building, source water protection, advocacy, that kind of thing on how to manage this issue, including regional HABs workshops. And many of you might have attended one of these workshops. We've had workshops in every single, I think, except for one region, so 9 regions, and we've actually gone back to a couple regions and had additional workshops. And the idea is to bring Safe Drinking Water Act and Clean Water Act folks together and start to integrate solutions for harmful algal blooms in these regions that make sense for the issues facing those regions. So that's just a bit of a summary of kind of the context of what we've been doing in the last couple of years. But just to provide even more context, I'm going to talk a little bit about the Drinking Water Protection Act. It was enacted in 2015, and it directed us to develop that strategic plan I was talking about before, to talk about a national plan for assessing and managing risks. And I'll mention this plan is very close to my heart. The Drinking Water Protection Act became enacted, I think, a couple of weeks before I started at EPA. So I began my career at EPA working on this plan. So I know it well, and it's sort of the convolution of a lot of my work along with colleagues of my first couple of months in the agency. So looking at the strategic plan here, I just want you to give you a sense of the sort of the breadth of information we covered in it. It is truly a roadmap for how we want to think about managing cyanotoxins in drinking water, from the short term, which this is, of course, an older document, now 2015. So many of these actions and many of the things that we discussed in this plan have already been done, and others are ongoing. They are more long-term in nature. A lot of that is our research and a lot of the development of different actions. So within the strategic plan, we talk about things such as going from assessing the health effects to looking at how to prevent HABs, and think about the causes of HABs, as well as when do HABs become toxic? Those kinds of questions that are ongoing we're trying to answer. Also, we've been trying to develop analytical and monitoring approaches and looking at assessing treatment options and those sorts of things. So I bring this to your attention just to let you know the context of where all these tools kind of fit in our larger plan. And this is obviously a work in progress. And so I'm going to present to you the tools we've developed for states and public water systems and tribal communities in order to start to get at that issue of how do we manage the risks of cyanotoxins and HABs in our drinking water systems. So I'm going to cover many of these in a little bit more detail, but not all of them. I did mention before this recommendations document. This is the document that we developed alongside those health advisories. And this document is meant to really provide a risk framework for how would you, in a risk management framework, how would you implement some sort of health advisory or some sort of action level for these toxins in drinking water. And then also we have tools from, how do you then develop a plan? What are the ways that you treat? So this water treatment optimization document for cyanotoxins is one I'm not going to go into a lot of detail on. My colleague Tom Waters and others were very instrumental in developing it. And I highly recommend, if you're interested in treatment, really going and looking at that document. It's just a wonderful, large degree of information in it. So I highly recommend taking a look at it. And the other thing I'm going to talk a little bit more also about is how do you communicate the risks? So how do you communicate the risks of this within your system before, during, and after a harmful algal bloom? And then also thinking about some of these fact sheets we've developed is a way, we developed this as a synthesized sort of bit of information on some of the funding sources available. So what are the solutions and how do you fund those? So we have a couple fact sheets on that, and then we also have a fact sheet on specifically for public water systems on some of the most important aspects of managing and background information on cyanotoxins and cyanobacteria in drinking water systems available. So I'm not going to show this video, but I would highly recommend folks take a minute or two to watch it. It's only about 3.5 minutes, I think. So at your leisure, think about watching this video. It does kind of talk about the issues of cyanotoxins and HABs, and does talk about these tools in a little bit more detail as well. I'll mention too, all these tools are available online. So digging right in to start sort of at the top of Many of these documents build on each other. We have a risk management framework that we're looking at throughout all of these documents. So I want to just spend a little bit of time talking about this 5-step framework for managing cyanotoxins. And many of you probably already have one in place or are familiar with this framework, but I think it's worth revisiting just because I think it does provide a great context for how these tools can be used. So within this 5-step framework, we include monitoring, treatment, and communication components in every step. And although this looks pretty linear, what I'm showing here on my screen, it's actually not a linear process. I think of it more of adaptive management, a circular process, where at any point during a HAB season or before a HAB season, you're in one of these steps, trying to prepare or trying to monitor or treat, and you're never sort of jumping out of this. It's a feedback loop, and you're constantly reevaluating and going back to 1 or 2 steps. So I won't go into a lot of detail on every single step, but I do want to mention some of the main components of each one. The first step is obviously very critical. Always start at step 1. So system-specific surface water evaluation. So this is looking at your vulnerability, really. And it's answering the question, are you vulnerable to harmful algal blooms in your source water and your finished water? And if so, when, how, what are the different pieces? And often this is a simple, have you had a HAB in your source water in the past? Often it's a history of HABs that puts you in a vulnerability category, but not always. So there's a series of different kinds of information you can look at. We do have that documented within I'll be talking about our cyanotoxin management plan template. We have that documented as ways to actually implement that evaluation. And then if you are vulnerable to HAB in your source water, so then what do? How do you prepare? What are the monitoring tools you need? What kind of treatment do you have available that you could, what are your optimization levers? And then also thinking about what are your early warning signs? So is it that you can monitor cyanobacteria, and as soon as you have cyanobacteria, you know that that's a kind of a red zone for you, or that you have chlorophyll A, or you have phycocyanin, or something that you're monitoring that triggers next action. And that next action would be monitoring for cyanotoxins in your raw water, and then making a treatment adjustments as necessary. So when you're doing that, if you're starting to see that cyanotoxins in your raw water, look to monitoring in your raw water and monitoring your finished water, and then making additional treatment adjustments. And then if you're seeing it within your finished drinking water, you want to think about more monitoring within your treated drinking water, and also more treatment adjustments and public communications, obviously at that point. But throughout these steps, you have a series of people that you're talking to, that you're getting feedback from. Hopefully you're making adjustments as adaptive management, so that you're circling back and you're constantly reassessing the risk and managing appropriately. So to put that into an actionable sort of document, rather than in in that flow chart or in our recommendations document, which is still a really great resource, we wanted to provide something that was actionable to public water systems and states to really get a handle on how do we implement this 5-step framework. And so this template, also available online, provides the 5-step framework in a fillable template. So all of it is customizable to your public water system, and it really helps to have that plan in place, because it also has context for who you talk to when, at what point in that step process. What kind of activity triggers a communication with somebody else, or triggers another treatment option, or triggers different kinds of action. So it's very helpful to have it so that you're not, that you're prepared and ready when things happen. And we understand through talking with many of our stakeholders and talking to public water systems that every system is really different. So we actually provide 5 example plans, so folks can get a sense of what are other systems doing, what have they done. And you'll see there's a lot of variety in how these systems are managing their cyanotoxins. They're all using that 5-step framework, but it's all very different in how they implement it, all getting to the same goal. So all of this is very customizable, but we think it's a great place to start. If you don't have a plan, you don't have to start from scratch. That blank page is tough. So I think this is our way to try to start to get at that. And I'll mention that all of our tools can fit into this management plan. So this is sort of your larger plan, and that treatment optimization document will really give you the tools necessary to start to fill out that plan. And then also this risk communication toolbox that I'm going to talk about here is also going to help you fill in those communication pieces. And I'll mention this toolbox that we developed. It's online, like all the other tools. And it is meant to be the way you communicate with the public. So the public is the audience, and it is not your plan for communication. So the plan for communication should be in the cyanotoxin management plan if you choose to develop that, or any of your other plans, because knowing when to communicate is very important, and that's the same thing as the things to communicate. So often the question is when to communicate. So having that understood up front is very important. And then this toolbox comes into play, where you have a lot of easy, again, customizable public releases, press releases, other kinds of like FAQs, fact sheets, a lot of different things that you can fill out that is already ready to go. And we recognize that many systems don't have their own communications department. Some might have their own communication materials, but for those that don't, this is sort of really easy, pick it up and go, and it is available in English and Spanish. Now I want to mention that within these materials, we're using our health advisory levels that I mentioned earlier as our example. So we are using this as a way to frame these actions, and also talking about communications as our communications points. So I have to just say, because I know it goes without saying, we have two health advisory cyanotoxins. We have two different populations and two different levels for both. So I want to just acknowledge the communication challenge. This is not the easiest thing to communicate. And what we are trying to do is find the materials that really help you communicate this and really help get the message across about what are the actions at these different levels that the public could take, and what does it mean? What do these levels mean? So that's really to get at the point of what are the ways we want to communicate this. And we have a couple different things I want to mention here. You can go on our website and find all these materials. But as I mentioned before, we have templates easily customizable, and you can use any action level that you have for your utility or for whatever your state regulations are. These are all customizable. And it includes lots of things that you just kind of plug and chug and go. So press releases that just need you to enter in your information that is specific to you, drinking water advisories, social media and text alerts. There are those that are ready to go and just customized to your situation. There's also other general information, some fact sheets, frequently asked questions, and then also graphics, as you can see here on the right, that really help with the multiple ways to communicate something, and that many people learn in different ways. And we want to just be sure that you have all the materials necessary to try to communicate these risks. And we have many different options for these graphics. So I highly recommend taking a look at it if you have a minute. So switching gears for a second, I'm going to talk about some of the fact sheets that aren't part of the toolbox, but rather these fact sheets are part of the more of the synthesis of existing information. So this is part of our looking at what are the solutions for managing HABs in your source water. So what are the ways you can prevent HABs in your source water? And then also, what are the funding options for managing cyanotoxins in your drinking water? That's where the Drinking Water State Revolving Fund comes into play. So these two fact sheets really summarize the opportunities for those kinds of funding. And if you were at Karen Worth's talk a couple of days ago, she would have mentioned a lot of these sort of opportunities and ability to leverage some of these opportunities. And these kinds of materials we have here are very specific to HABs. So I think what provides a lot of interest for folks that are dealing with HABs on a regular in their systems is that this is very tailored to HABs and talks about case studies and state examples of things that have worked and ways that people have leveraged funding and ways they've used the Drinking Water State Revolving Fund for a variety of different actions related to HABs in those source waters, and then also managing the cyanotoxins in the finished water. Another fact sheet I want to just draw your attention to, because it's recently updated. So if you're someone who's looking at our materials all the time, I'm happy somebody's doing that. And I want to just make a note that we have updated this June 2019, that we updated this in June 2019. This was an older fact sheet that this is different from the fact sheets that I discussed as part of the risk communication toolbox, and that those fact sheets were really geared to the public. This fact sheet, the public water systems that are the entire audience here, to try to give information in one spot on the health effects, analytical methods, treatment approaches, and there are links to additional information within it if you just want a quick reference guide for wherever you're dealing with at the time, and you just want to figure out what's the most important information. This is a great resource for you, so I highly recommend taking a look at that. And one thing I'll mention is that what I've discussed in the last couple minutes here is part of a larger picture, as I mentioned, from the strategic plan standpoint. We have ongoing HAB activities across all of EPA, and a lot of it, hopefully you had a chance to see Nick Dugan's great presentation a couple of days ago, where he talked about treatment approaches and source water treatment impacts. So we have that ongoing research happening. We have ongoing research on the health effects, ongoing research on toxicity, research on predictive modeling, including tools that might be helpful to public water systems begin to understand and predict when they might have a HAB, and also looking at some of the cost-effective source water protection measures. And we have ongoing activities on not only just the research, but also on our source water protection partnerships, and also looking at how to build those bridges between the source water piece and the finished water piece through our regional workshops. That's sort of an ongoing integration effort. We're trying to look at this issue in a holistic fashion. And we have colleagues that are also working on recreational water quality issues, we have recent advisory numbers for that that's been published. And so a lot of ongoing work. And so the work's not done. We are still following that roadmap, that strategic plan, to try to figure out the best ways to manage this at a national level. So with that, I just really want to take a moment to thank you for spending the time to listen to this. And I want to open it up to the fact that I am available at any time for questions if you want to reach out. And also want to be sure you see our websites here. There's a cyanotoxin and drinking water website that's very specific to the information I talked about today. And then the CyanoHABs website, which is our overall HABs website for the entire agency. It is just a huge amount of information and great background information and other information there. So I highly recommend you take a look at that. And I really want to thank you all for spending the time today, and I will turn it back over to Darren.
All right, thank you very much, Katie. Okay, so we'll go ahead and move on to our next speakers. And just as a reminder, feel free to put your questions into the question box, and also too, as a reminder, the handouts are available. The speaker bios, which I'm going to really shorten up, are on that site. So I suggest that you take a look at that for the full bios. So you're going to get 2 for 1 here. Our next speakers are going to talk about ASWA's new source water PFAS toolkit and guide. And Deidre White is a project manager with Association of State Drinking Water Administrators, or ASWA, and they're co-sponsoring this event, of course. And then Ashley Arias is an environmental associate with and a project manager with Cadmus Group, and of course they're helping us run this program as well. So I'm going to turn it over to Deidre.
Thanks so much, Darren. All right. As Darren said, I'm Deirdre White with ASWA, and I'm very glad to be sharing our presentation during the workshop session about ASWA's PFAS Source Water Protection Guide and Toolkit. So I'll start with a few slides to provide some background information about why ASWA did the project, and then I'll turn it over to Ashley Arias with the Cadmus Group, our contractor, who will walk you through the toolkit sections and content. So for those of you who are not familiar with ASDWA, our mission is to protect public health and the economy through the provision of safe drinking water. And our members are the Drinking Water Program administrators from the 50 states, territories, the Navajo Nation, and DC, who provide public water system oversight in the form of regulation, technical assistance, and funding with the Drinking Water State Revolving Fund. And we also coordinate with multiple partners. We consider ourselves co-regulators with EPA, and we work on PFAS and many other drinking water issues with all the other state environmental associations such as ECOS and AQUA, as well as water utility associations. And the purpose of our presentation today is to showcase ASDWA's new PFAS Source Water Protection Guide and Toolkit. And this is just one of many white papers, reports, resources, and tools that ASDWA has developed and posted on our website to help meet the needs of our members and also share information with many other stakeholders. Because PFAS has caused widespread contamination across the country, the purpose of this tool is to demonstrate and share effective strategies that some states have used for addressing PFAS contamination risk in source waters. And this tool helps to inform policy decisions for state drinking water programs, water utilities, and other organizations to determine actions that they may or may not want to undertake to assess and address PFAS for protecting public health. And it also encourages collaboration and communication with state and local partners. And so why we did this project? Well, ASDWA has a PFAS work group that includes members from many state drinking water programs from across the country. And the work group has been very active on writing comment letters to EPA and helps to set priorities for ASDWA's PFAS efforts and actions. And it was this PFAS work group that identified the need for this project. And because while some of our states have set their own PFAS standards and conducted monitoring and cleanup actions, this project is really aimed at providing guidance and sharing examples for the many other states that are considering actions or are in the early stages of investigating sites with potential PFAS drinking water impacts and understanding the scope of potential PFAS contamination within their state. And this is a tool for more than just the state primacy agencies who are ASDWA's members. It is also for water utilities and communities who can use it to update their source water assessments and GIS maps to prioritize locations for potential PFAS monitoring and sampling to identify sources of PFAS, and then if needed, conduct investigations and remediation actions based on known uses of PFAS in business and industry, as well as pathways for fate and transport. And I want to say thank you to the Project Advisory Committee members listed here from 9 states who provided input on the project and are doing this work on the ground in their states and understand the needs for assessing and addressing PFAS at the state and local levels. And thanks to all the many more states that provided examples of their PFAS efforts that are included in the toolkit. And with that, I will turn it over to Ashley Arias of the Cadmus Group.
Thanks, Deirdre. Good morning and good afternoon to everyone on the webinar. I'm Ashley Arias with the Cadmus Group, and I'm excited to share some additional details about the guide and toolkit, also provide a brief demonstration of the recently launched tools. So first, I want to quickly thank ASDWA for the opportunity to partner and support this important work, and EPA and ASDWA for inviting us to present today on the webinar. Our goal for today is to share the new guide and toolkit with you, to present a demo of the decision to support tool, and to answer any questions about these new resources. We'll showcase the major components of the toolkit, including the technical appendix, mapping guidance, and an Excel-based decision support tool. We'll also share information about some additional resources that were developed to supplement and enhance the toolkit and support feature updates for the tool. We'll explain what each resource contains, how they were developed, and the primary uses and benefits to state drinking water programs, as well as the other partners that Deirdre mentioned who may be interested in using this toolkit.
States are in different stages with PFAS right now, so we really wanted to focus on developing some user-friendly resources and tools that are accessible and that states, water utilities, and other partners can benefit from regardless of their different stages in understanding, identifying, testing, and taking action to address source water vulnerability and possible PFAS contamination. So the first element we'll talk about is the technical appendix. This is a 70-page document which acts as an appendix or complement to the decision support tool, which we'll take a look at a little later. The technical appendix includes 3 main sections. The first is chemicals of concern. This section synthesizes key information about what we know about the PFAS group of chemicals. This includes information on chemical and physical properties, toxicity, fate and transport, and which PFAS chemicals are monitored under ECMR, as well as possible options for expanding monitoring based on that toxicity information and how they behave in the environment. The second section is PFAS in the United States. This provides a brief history of the uses of PFAS and how it's been regulated in the US. It also contains a discussion about PFAS in firefighting foams, which some states are working to address specifically, and information about the PFAS life cycle from production to waste treatment, as you can see on the screen here. This section contains a list of North American Industry Classification System, or NAICS codes. These classify businesses by their type of economic activity and can be used to help monitor for use and storage of PFAS by industry. These 2 sections in particular were developed utilizing academic literature reviews, information from organizations including the Interstate Technology and Regulatory Council, the Agency for Toxic Substances and Disease Registry, the EPA, and with input from the PAC members that Deirdre mentioned before. The topic of PFAS can be overwhelming because it's so broad and the landscape of information and what we know is constantly changing. So the technical appendix can help readers by providing somewhat of a crash course on PFAS. They're by no means comprehensive. They're pretty short sections, but they distill a lot of information into a succinct introduction to PFAS and can provide information that may be beneficial for readers or users that want to be able to access the other elements of the toolkit. The last section is the state profiles. These are individual profiles for 27 states and territories. These profiles make up the bulk of the technical appendix and provide a breakdown of activities that states are undertaking to address PFAS in source water. The purpose of these profiles is for readers to be able to concisely learn about what a state's doing or has already done to address PFAS, and each profile follows a similar format with 2 to 3 programs listed at the top and expanded descriptions for each of those. And then below, there's a table highlighting programs, relevant resources with links to those. The state profiles were developed based on a survey that was distributed to all the states in summer 2019. And then states had an opportunity to review their profiles in January, February 2020. So the information in the technical appendix and that was used to develop the decision support tool is current as of early 2020. And there will be opportunities for states to submit updates and additional programs to ASDWA for future versions and updates of the tool. There are a few parts of the technical appendix that may be particularly helpful to those of you watching today. Everything you can find in the decision support tool is also included in the technical appendix. It can be a good resource to browse, get a sense for the work going on right now in the US, and in the resource tables within each state profile, such as the one shown here. Each state has organized their relevant programs, initiatives, and resources, making them easy to access and use. These resources include case studies, standards and regulations, maps showing how PFAS data can be displayed geospatially, sampling plans, test results, and information about certifying labs to test for PFAS. Each of the resources is categorized, linked, and also includes a brief description of the resource, as you can see in the table here. Since the resources have been systematically categorized, you can also search through the document to find related types of resources. Readers may also find the additional information about NAICS codes and the list of NAICS codes in Part 2 of the technical appendix to be helpful for future planning efforts. Each of these codes is tied to a manufacturing process or economic activity. So if you're looking for possible sources of pollution, then using these codes could be helpful. And we'll touch on this again when we look at the mapping guidance. The list of NAICS codes in the technical appendix and mapping guidance was compiled by states who have or are already using NAICS codes as part of their sampling and monitoring plans. So we tried to amalgamate a list of all of the NAICS codes that have been used in hopes that this list could be helpful for identifying possible sources of PFAS pollution in the states. Next, we're going to move on to the second element in the toolkit, which is the mapping guide. So the mapping guidance was developed to help readers who are interested in using GIS data to complete a screening level assessment of source water vulnerability to PFAS across a state, county, or other geographic area. The guide starts by presenting a general framework for assessing source water vulnerability to PFAS, and then the remainder of the guide describes potential data sets that could be incorporated into a source water assessment. These are primarily national data sets that are maintained by federal agencies, but there are some examples of state and local data sources to help identify if there are additional sources within your state or locality that could be used. The sections are organized by data sets that help identify PFAS source locations, such as the EPA Facility Registry Service, the FRS, and PFAS monitoring data, such as the EPA USGS Water Quality Portal, as well as watershed and aquifer data sets, which indicate environmental characteristics relevant to PFAS fate and transport. The watershed and aquifer data sets described in the guide specifically address watershed and aquifer boundaries, as well as land cover and soil and geological attributes. Something to note about the FRS and its summary that's included in the mapping guide is that it contains facilities that are subject to EPA regulations and permitting and stores the NAICS codes that we mentioned before for each facility within the database. Because of this, they can be used to map facilities that are producing or handling products such as waterproof fabric or non-stick coating. This slide displays the source water assessment framework that's outlined in the guide. So step one, the approach starts by defining the purpose and goals of the assessment. This means making clear and specific decisions about which source water types are to be assessed and the geographic area of interest. Step one also involves clearly defining the desired outputs of the assessment and application. Then we move to step two, where the goal is to map the source water locations that are selected for the assessment. The third step involves mapping potential PFAS sources. These could include locations that either produce, use, or store large quantities of PFAS. And the goal here is to identify higher risk locations for PFAS exposure to the surrounding environment. Step four, PFAS monitoring data is mapped to identify source water with and without detections. So source waters with PFAS detections could be readily classified as vulnerable and then prioritized for follow-up monitoring, analysis, and management. Then step five, watershed and aquifer data are mapped to identify areas with higher risk. So high risk characteristics could include areas that are prone to surface runoff and erosion, or areas with shallow groundwater or higher rates of groundwater recharge. The final step, step six, pulls all of that information from the previous 5 steps together to classify the vulnerability of the source waters in your area of interest and to then identify priority source waters for next steps for management. Detailed methods for all of these steps will depend on the specific goals, resources, and the data that's available for an assessment. So what we've tried to present in the guide through this framework is a general outline for a source water assessment that can be expanded on and customized based on your own situation. For those asking, where do I start with a source water assessment? The mapping guide can provide a framework for key steps to characterize PFAS vulnerability and to identify priority source waters for monitoring and management. The guide also includes descriptions and links to those national data sets, which can be used to supplement and enhance the national data sets, as well as some of the state examples, which can be used to supplement and enhance the national data sources. The guide also includes the same list of NAICS codes that are in the technical appendix and that list of state databases that could be considered. The last element in the toolkit is the decision support tool. So now we'll transition to looking at the support tool as well as some of the supplementary resources that were developed as part of the project. Included in the toolkit is this communicating with industry fact sheet. This came from discussions with the PAC to have more guidance on working with communities, working with industry, communicating with industry about PFAS contamination. So the Communicating with Industry fact sheet includes some background information that you see here on working with industry, things to consider when talking about PFAS contamination, particularly with industry representatives. And then the majority of the fact sheet is this series of questions. It's in a fillable PDF format, and the intention is to allow you to develop your own plan for working with industry. So it asks some questions and provides some options for things to consider with who you're reaching out to and how you might want to phrase or approach communicating or working with industry representatives. In addition to Communicating with Industry fact sheet that's up on the screen, we also developed a tool update form for states, and we'll take a quick look at that when we dive into the tool. That allows states to identify either updates to existing entries in the tool or to submit new entries. So as the landscape changes and as the work that you're doing changes, you can submit updates for the tool. Here's a quick overview of the decision support tool, and then we'll jump into the demonstration. So decision support tool is an interactive Excel-based decision-making tool. It helps to provide guidance to state drinking water personnel and other partners for addressing PFAS contamination. The tool contains two search engines, which are the bulk of the tool. The first one is shown on the screen here. The user answers a question about what aspect of PFAS they want to learn more about, and they can select from PFAS basics, locating PFAS, testing for PFAS, and taking action to address PFAS. If they select taking action, there are additional options that appear that you can select from to tailor the information even more. One of those actions is outreach and communication efforts. So if you're interested in learning more about what other states are doing before you try to develop your plan for communicating with industry, that could be a good place to start. In addition, the form includes an option to see a certain state's results first, as you see here at the bottom. So if you're interested in seeing what initiatives your state has, or a neighboring state or state that you've been hearing about recently, and the efforts that they've been undertaking, you can do that and you'll get those results first in the response. There's another form, which we'll share in the demo, that also allows users to get results based on the specific category of resources. And those are related to the table that I shared when we were talking about the technical appendix. So things such as case studies, fact sheets, or state websites, as well as specific types of PFAS contamination. Those are pretty limited in the tool, but things such as firefighting foam or consumer product contamination. This means that if you know the type of contamination that you're concerned about or that you're dealing with, you may be able to find some specialized results across states or for a particular state and see those relevant resources. The information that's presented in both results pages is sourced from the technical appendix document, and some information is also pulled from the mapping guide. Most of the resources included in the decision support tool came directly from the states and are from the state profiles. The information from the technical appendix and mapping guide was categorized into these easy-to-use groupings so that users can filter down to the information that's most relevant to them in their current stage of dealing with understanding, identifying, testing for, or taking action to mitigate PFAS contamination in source water. Here we have the results page for this, which shows you your tailored results that are specific to the decisions that were made. So next, I'm going to transition into the tool. To access the tool, you can go to ASDWA's PFAS website, which you should be seeing on my screen now. From here, you'll find some background information on the tool, as well as links to each of the individual components that we just talked about. At the bottom of the page, there's a link to download the guide and toolkit. If you click on that, it'll download a zip drive, a compressed folder with all of the resources that we just talked about that are included as part of the tool. It looks something like this. And you can access the decision support tool, fact sheet, mapping guide, or technical appendix from that folder saved on your system. So now jumping into the tool, to access the tool, so after you've accessed the tool and it's been saved on your system, you'll be able to open it. This is an Excel-based tool. We selected Excel because it's readily accessible to most users. It's user-friendly. Most people are pretty familiar with it, and it can accommodate updates pretty easily, and that was a high priority for the PAC and for the team working on the tool. We're going to take a look at a few different aspects of the tool and run through a few scenarios to demonstrate the features and key functionality of the tool, while also showing the type of results that you can expect to receive when you're using the tool. Here we have our home screen. Within the home screen, we see our a little bit of background information at the top here on the project and how the decision support tool was brought together, the intention and goal of the tool. Then we have these links to our different filter resource options, our our entry forms that we just shared. So we can filter resources by PFAS topic of concern. We can filter them by document type. We can filter by contaminant source. And then we also have some additional helpful information here at the bottom of the home screen, where you can look at tool definitions that are used throughout the tool. And there are links at the bottom to the technical appendix, the mapping guide, ASDWA's website, and to the fillable form. So if you are in the tool and you notice that there's some information about your state that's out of date, or if you would like to add something, you can just click on that from directly within the tool. It brings you to this PDF, which you can download, fill in, and then the bottom of the PDF file has a button to email your updates to Deirdre to get those in the queue for consideration for updates to the tool. When you're in the tool, you'll also notice that it'll let you know when the tool was last updated, and you can view additional information, some acknowledgements. So we're going to jump into the filter resources by PFAS topic of concern. You can navigate there from either the links on the homepage or from the tabs at the bottom of your Excel worksheet. If we take a look at the color coding here too, you can see that our filter resources by PFAS topic of concern are coordinated blue with your entry field and then the specific results that you get back. And then we also have our filter by resource type and source, which are combined. They're one form. They are here in green, and then we have our green tabs at the bottom. So if at any point you're unsure of where you are in the tool or where you'd like to go, you can use the tabs at the bottom or just return to the home page. If we go to filter resources by PFAS topic, this is the form that we showed on the PowerPoint. So here there's an introduction, some explanation about how to use this form, and then you can select what PFAS response you're most interested in viewing. So if you're just getting started and you'd like to see what materials are included in the tool that cover PFAS basics, and these could be things like state websites, fact sheets, or guidance documents, then you can make the selection. If you'd like to know a little more before you make one of these selections to determine which area you're most interested in viewing, you can always go to the Tool Guidance and Definitions tab, either by using these buttons in the top right or going to the tab in the bottom of the Excel. Those will take you to the last tab, and this provides a little more information on the criteria summaries and how criteria were defined in order to categorize resources into those criteria. If we go back to our entry and we leave PFAS basics as it's selected, we see here the second part, selecting a state to prioritize. I'm going to leave this unselected for now. Something to note is that not all states are included in this dropdown. You can select to return results from every state, or you can select to prioritize a particular state. The states that are included within the dropdown here are those that have profiles in the technical appendix. So as additional states may be added to the technical appendix or additional information added to the tool, that list may change, but right now it would contain the 27 states and territories that are included in the technical appendix. Here we're going to press submit at the bottom of our form. And what we get taken to then is our customized results page. So we see at the top of the page our selected criteria. As a reminder, we had selected PFAS basics. And then that description definition of PFAS basics is included here at the top as well, so that you can get more background information and detail on the type of resources that are now going to show up in your table. Within the table, we have resources and links, so resource title and a link to that resource, the state if it's state specific or national if it's not, and then a brief description. So from here you can scroll down through the results that you received and click to view particular resources. That'll take you directly to the state website or the resource. if you decide from reading the description that's something that you'd like to take a further look at. From here, we have some helpful buttons up at the top where you can return to the question, you can view that tool guidance and definitions, or you can follow in the instructions to download your results as a PDF. The other thing I want to share in the filter resources by PFAS topic is that while PFAS basics, locating PFAS, and testing for PFAS are single click answers, if you choose to select taking action to address PFAS, then it'll open up this Part 1B question. And this is to identify which actions you're specifically interested in identifying resources for. So if you're looking at taking action to address PFAS and really what you're most interested in is seeing what other states have done to create a state action plan, you can go ahead and select yes in that dropdown and rerun your report, and it will completely update to your new selected criteria. So in this case, our selected criteria are taking action to address PFAS and creating state action plans. And we have our summary of that new updated criteria here. The same type of results organized alphabetically by state. If there aren't any national results, they'll just be organized alphabetically by state. Otherwise, the national results will come first and then they'll be alphabetical. When you are selecting from taking action to address PFAS, you can make multiple selections here. So if you are interested in what states are doing to interpret results, create state action plans, and their outreach and communication efforts, what you'll get are all of the results for all of those categories. So it's inclusive, it doesn't limit, you don't have to, a result doesn't have to meet multiple criteria. And then here, if we select a state to prioritize, I'll select Colorado. Then we see that we have our selected criteria, our actions summarized again, and first we see our results from Colorado, then we see our national results and alphabetical by state after that. There are a few tool tips and notes that'll appear at different times during the tool. This note is letting you know that although you selected multiple criteria, the summary that's being presented here is just for the first criteria that was selected, but you can always go to the tool guide and definitions tab to view definitions and additional information about the other criteria that you selected. In the last minute here, I'm just going to take a quick minute to show you the other part of the tool. This is to view particular types of documents or sources. It's set up very similarly to the first form, and you can select from multiple document types. So we could select case studies and fact sheets here. And then if we ran our results, we would get all results that are case studies or fact sheets across every state and the national resources in the database. If we are interested in learning more about a particular source, we could also add a filter option here. So in this case, we would get results for all case studies and all fact sheets that are included in the database that specifically address firefighting foam contamination. If I submit my form now, we'll see that we get results, national and state by state results. And again, our criteria are summarized with the document types that we selected, case studies and fact sheets, and the source of PFAS that we selected, firefighting foams. Again, similar tools up here in the right for you to return to your question to change the criteria, for you to view the tool guidance, or to download this version. And all of these links take you directly to the state websites or the resource that's being reviewed. So now I'm going to briefly return to the presentation to just close things out. And first, I just want to thank everybody on the line today for your time and attention, for having us come, EPA and ASDWA for having us come and present on the toolbox. As Deirdre said, there was a whole team supporting this effort, including all of the PAC members, other states who contributed their resources, input, and reviewed their own state summaries, and our team at CADMAS. All the toolkit materials that we share today are currently available on ASDWA's PFAS website, and we encourage you to take a look, download the toolkit, and use the guidance and decision support tool to complement your existing efforts. You can contact Deirdre or myself if you have any questions, and we'll take questions in the next part of the session. And then here's the ASDWA.org PFAS website, or this QR code will take you directly to the site where all of the tools are hosted.
All right, thank you, Ashley and Deirdre. Okay, well, now is the time that we go into some Q&A. It looks like we have about 25 minutes or so. This is where I have to go back and forth. So if I'm looking off the side here, I'm trying to go through the questions that have come in, and we appreciate those. It looks like Simone, we're heavily weighted towards the arsenic side of things at the moment, but again, you know, people will continue to put in your questions. So it's interesting because I have seen that myself anyways, kind of a resurgence in questions about arsenic these days. I've been telling people I don't know what's going on, but you know, arsenic has definitely it's definitely become, we'll say, popular in terms of technical assistance that at least I do as of late, and maybe that has to do in part because Tom Sorg is retired and I get all these questions. I don't know, but anyways, let's go through some questions here. So do we have all the panelists? Do we have? There we go, Katie, and we get everybody's faces up there. There we go. Okay, so we'll start with some arsenic questions. Let's see here. So I think you sort of showed this in your table, Simone, but what treatment techniques were used dominantly in the case of pattern C systems?
Yeah, that's a great question. And I do apologize because I shared my slides early on to be disseminated to everyone, and then I added more information in it. So I will make sure to share the additional information so that you all have that table with the different treatments. So the B and C systems, and especially the C pattern systems, were mostly iron removal systems. I think it makes sense because they're more complex just by default. So the arsenic treatment is selected, you know, a big criterion to select arsenic treatment is your source water information, how much arsenic you have, and iron. So the iron removal systems, they're called iron removal, obviously, so they have a lot of iron in them. You're hoping that by removing the iron, you're also removing the arsenic that comes along with it. But the more of that stuff that you have, the more complex situation you have, and you may have potentially more spikes and more absorption opportunities in the distribution system, pipe materials, and then more complex release mechanism. So it was generally iron removal systems, a few in coagulation filtration, I think, but I'll share the detailed list with exactly how the groupings are so that you can see them. And of course, the pattern A systems tended to be the simpler adsorptive media systems, which adsorptive media is usually used when there's low iron in the water. So then the systems with adsorptive media treatments, you know, were simpler in the sense that they didn't have as much of an iron load. So it really does make sense if you think about going back to the treatments. And I do apologize that I didn't share source water information for arsenic, iron, and manganese, but that was all available to us. And you can see how in the paper, I'm gonna try to share the paper too, Darren, if there's a way to figure out the specific participants who asked for it. And then you can see exactly the higher iron coming in the iron removal systems, for example, compared to the adsorptive media systems. But that's a good question. I think a lot of people were worried about pattern C.
Yeah, there was a couple of questions actually that, yeah, they look like they were the same actually. So, okay. Next arsenic question. Does the water have a memory of its arsenic content for such reversals to happen in the homes?
You know, that's a good question. I think overall the distribution system itself does. So distribution systems don't like change. There's some sort of equilibrium that happens where all the pipe materials with the water that has been flowing through react in certain ways to establish, you know, those mechanisms of accumulation, and everybody's kind of happy with that equilibrium. So each time you change something, there's always the potential to disturb and disrupt that equilibrium, and for those reactions to go either way, like to be reversed and to go back to what was happening. So when arsenic treatment started in the source well water, well, that disrupted, you know, the quality of the water coming into the system. There was less arsenic coming in, but it also disrupted the scales that were in contact with that newly, you know, the newly treated water that caused more arsenic to be released from the pipes back into the water. So it's not just, you know, the memory of the water itself, it's the whole equilibrium of pipe materials that water is flowing through, and the the quality of the water that changed that was flowing through them? That's a great question.
Okay, thank you, Simone. So, Katie, got one here for you. Has any research results indicated what factors determine if cyanobacteria produces cyanotoxins?
Yeah, so that's a wonderful question. And there's a lot of research out there to try to figure out what causes the trigger for the toxins. At this point, there's a lot left to be known. We do know in some cases, if you do have an abundance of cyanobacteria, you may have a higher risk of toxins, but often the toxins are very sporadically, they could be actually the genes could be there to actually produce toxins, but they don't actually do it. We don't know yet the triggers for those situations. We can only try in terms of resource managers to think about when your risk is highest. And sometimes you can, for instance, I know in some systems they see the cyanobacteria bloom happen, and then within 2 weeks they're seeing the toxin produced. They're seeing that as something that happens in their system, but it is not predictable at this point. We do have research that's ongoing to try to figure out what those triggers are. All that can be done at this point is to manage the risk and to think about how do you do some targeted monitoring to figure out when you might be more likely to have toxins to verify that you have them. It's a great question and needs more research.
Good. Okay. Thank you. Another related HAB question. Do you know safe chemicals that can handle cyanotoxins? I think you're talking about oxidants, perhaps.
Is that for source water? I'm thinking.
I assume that's what that means. Source water protection. Or treatment.
Source water. Yeah, for treatment, we know what the treatment, conventional treatment can actually treat the intact cells. The extracellular toxins, if anyone was at Nick Dugan's presentation, we know that we need more oxidation and absorption to deal with those in a lot of cases. So you're looking at your ozone, you're looking at PAC, GAC. These have been effective in your treatment system. When we're talking about chemicals in the source water, a lot of people are using copper sulfate, but there are unintended consequences of that, as well as the peroxide is something that is used frequently in the source waters. There are unintended consequences of using those in your finished drinking water. I know Nick covered that a little bit in his presentation. At this point, a lot of what we talk about, there are chemicals, but one of the bigger things is, how do you prevent these? And also when you do have to use chemicals, the timing on it is really critical. So you want to be using chemicals not at the real height of your bloom. Otherwise, you're going to have a lot of extracellular toxins out there. So we don't have any particular information on, best practices for chemicals. We do really talk about preventing being a big important thing, but many utilities have used chemicals safely, but we don't have a lot of information on, what we might recommend. I know that we do have other stakeholders looking at those kinds of strategies for mitigation. There's other more physical strategies you could use, mixing, other kinds of things that might not be as invasive as a chemical, but we do have some availability of some of those treatments and the consequences on our CyanoHabs website under the Managing and Mitigating Blooms section. So I encourage folks to look at that as well.
Okay, thank you. Let's see, Ashley or Deirdre, I think, is the ASDWA toolkit accessible to others? And if so, guidelines to access these. What are the guidelines to access these?
Yeah, I can cover that. So yes, it is available free of charge to the public for anybody who wants to download it from our website. That link that Ashley provided, asdwa.org/PFAS is where you can find it.
Okay. Another question for the two of you. In the mapping tool, where do the wellhead protection area layers come from?
I can take that, Ashley, too, if you want. So, so the wellhead protection area layers would come from either the state source water assessment or the water utility maps. There is also a link in the mapping guide to DW Maps, which is an EPA tool that includes the wellhead protection areas by density of wellhead of wells. So you could look at that too if you are someone who does not work directly with the state or the water utility. Ashley, did you want to expand on that at all?
No, I think that's great, Deirdre. Just gonna say that within the mapping guide, there are a lot of data sets that are referenced or mentioned that you can take a look at. It's really more of the providing the framework. And so those, as Deirdre said, those GIS data sets for wells, intakes, source water protection areas are typically maintained by state drinking water programs or water utilities. So that's where you would access your own layers in order to implement the approach for yourself.
Okay, thank you. Go back to arsenic. Here's one for you, Simone. For small groundwater systems, do you have any suggestions for good strategies for managing backwash waters for arsenic treatment?
Well, you know, that's a great question. I wish I had a very specific answer to help you out here. What we're trying to do in this research project, and remember, I'm coming from the Office of Research and Development, which focuses on research, not necessarily, you know, management and regulations that have to do with all of these things. But the idea is to look at the chemical composition, maybe hopefully move into the quantity aspect to hopefully give you the information that you could then use to make some of those management decisions. I know that from the reports that I've read for all 50 systems, and they've all, you know, done different things. It's definitely been a challenge. It was one of the key topics in the initial survey, how to manage residuals, and even after in the later survey, more than 10 years after the initial survey that Tom Sorg, who spearheaded the arsenic demo along with some others did, it was still, you know, one of the remaining problems. I did talk with some systems. I heard about how they handle backwash and residuals in general, but it seems like there's a lot of different approaches that are really oftentimes dependent on local regulations as well. It's not just the federal regulations, it's local restrictions. It may also be like restrictions they have, for example, in terms of availability of land, for example, to dispose things in an evaporation pond. Some systems don't have that surface area available to them, for example. So it's really complicated, and I think it kind of has to happen on a case-by-case basis, depending on what's available to you and the resources that you have, combined with all the federal and local regulations that you have to deal with. I wish I had a better answer for that one.
Well, since you said I could respond because I was a co-author, maybe I just add to that. I've always felt for as long as I've been with the agency that residuals is just an important topic that we perhaps don't address, you know, as well as we could, because as Simone said, a lot of the treatment, you know, decisions that we make in this arsenic demo program, I mean, really, the first thing that was asked is what kind of residuals are associated with the treatment, and then from there, you know, treatment approaches were eliminated because there were limitations on disposal. So dealing with residuals, minimizing residuals, reusing, whatever. I mean, these are all topics that I think, you know, there's some work, and we've done some work ourselves, but it's been just a very touch the surface kind of thing, looking at, you know, microwave heating and other things to try to minimize the volumes of residuals. But I really, really believe that, you know, down the road, we're going to have to address these residual issues, you know, because they don't go away, and of course they contain concentrated contaminants and things like that. So more work needs to be done in this area for sure. Let's see. Says here, so what treatment system, this is back to another arsenic question, what treatment system is the best for arsenic, iron, and manganese removal? And then what is absorptive media used for?
All right, well, great question. So, you know, these are all questions that the initial arsenic demo handled. The point of it really was to look at the efficacy of each treatment system, and at least the options that were available back then. The purpose of our project here was not necessarily that, which had already been handled, but it was just to compare what was coming in versus what was going out, regardless of the treatment, although selection of the treatment was associated with source water quality, so it was actually related to some of our conclusions. But in general, adsorptive media was used in the majority of systems in the arsenic demo, and those were, again, simple systems where there was low iron and manganese coming in, and the adsorptive media were used to remove the arsenic. When you have iron coming in, if it's a lot of iron coming in relative to arsenic, so there's the ratio that is calculated. If it's more than 20:1, so there's substantial amount of iron, then your best chance is iron removal. And the whole point of that is by removing the iron, really you're removing all the arsenic that's also attached to it. So that's your best case scenario in that case. If you're in between, you have relatively high arsenic, more so than you would have for an adsorptive media system, but it's below the 20:1 ratio, then other treatment options may be more useful to you, like coagulation filtration, for example, where you actually add ferric chloride to increase your iron levels so that you can then more efficiently remove arsenic along with the iron that you've added. So this is just a very high level overview. Darren, I don't know if you want to add something.
Oh, no, I think it covered it. I mean, the residuals discussion comes into play too, and what, the iron you have in the source water, and I think you said it well. Okay, thank you.
Sure.
Katie, which is more effective and cost efficient for cyanotoxin removal, PAC or GAC? So powder activated carbon or granule activated carbon?
It's a great question. Always want to know which one's more. Yeah, they're both very effective. I'll mention it depends on your system for what's going to be most cost effective. The upfront, in a lot of cases, capital cost to put in GAC is pretty high. And also maybe not a possibility for, given the size of the footprint of the utility. PAC can be easily fed for conventional systems, but if you have, for instance, a slow sand filter, it might be a little bit harder. So I hate to say this, but it kind of depends. They're both very effective and both things that we find to be successful for many utilities. And I would just mention the treatment optimization guide document that I discussed in my presentation that's available online can go into some of those pros and cons. And if there are specific questions that people have about their utility, we are always happy to discuss those. And please reach out to me and we can discuss in more detail about your particular situation.
Okay, thank you. And another question related to algotoxins. Have you seen toxin detection when no visible bloom was present?
That's a great question. Yes, we do. A bloom can be present and there are no toxins, and there can be toxins present and no bloom. And there can be a bloom and yet no toxins as well. So yeah, the thing about toxins is that they can move throughout the water column as well. And a bloom can move in and out, like the visible bloom can move in and out based on wind, and the toxins can stay for weeks. So it's possible that you have a bloom that maybe your actual visible bloom has dissipated, but for weeks later, you are still seeing toxins. So that visual observation doesn't always lead to knowing whether or not you have toxins or not, which is really, the visual observation is one good tool, but there are multiple other kinds of screening tools you can use to see if you might have toxins in your water column and in your intake. So yeah, that is a really great question and one that isn't as intuitive, the answer. So it does make managing the risk a little bit more challenging, but knowing that's true really can help you start to get a sense of, when might you want to monitor to be sure there aren't residual toxins from a bloom you were able to see. And sometimes you might not have ever been able to see that bloom, and there are also benthic blooms as well that you may never have seen. So it really does point to the need to really understand your water, your source waters, and having an understanding of whether or not you have a history of toxins is a good start.
Okay, thank you. Going back to arsenic, Simone, does soluble arsenic refer to arsenic-3?
Yes, great question, because arsenic speciation is very important in terms of mobility and toxicity, but also treatment choices that we must make. So The soluble arsenic that I mentioned in some of my slides, I showed you graphs of soluble versus particulate, for example, for arsenic and for iron. Those actually refer to just the standard syringe filtration to a 0.45 micrometer pore size filter. So this is just the operational definition for dissolved versus particulate. So if you have your water sample and you pass it through, what comes out is the dissolved concentration for arsenic, iron, and other inorganics, and what was retained is the particulate. So no, the definition has to do with the 0.45 micrometer filtration. Now, after you've done that filtration, what comes out is your dissolved arsenic level. You can pass that water that passed through the filter to a different kind of resin, and that then tells you the speciation between arsenic 5 and arsenic 3. So that's another step in the process. What you've gotten from the initial filtration for soluble could be, depending on your pH and the oxidation reduction potential of the water, could be arsenic 3 and 5 or one or the other. But in order to make that distinction, you would need to go to the second step with the resin. The resin retains the arsenate, which is arsenic 5, and lets arsenic 3 pass through. That's a good question.
Okay, thank you. I have another arsenic related question, although I can't find it, but I sort of have it in my mind. I remember it. Do you have any recommendations, Simone, for water systems where a change is made like this, and how and what to look for in the distribution system to kind of, you know, identify such an issue here that we're talking about, and maybe preventing it?
Yeah, you know, that's a great question, and we've been talking about it a lot. Certainly, the monitoring that we typically do, you know, is associated with regulations, which again, most of the time stop at the entry point, unless we're talking about lead and copper, which are regulated at the top. For example, if we really want to know what's happening within the distribution system, we need to be sampling the distribution system. Some of the alternative monitoring approaches to do that would be to collect tap water samples, for example, like in the arsenic demo that we analyzed. Other approaches are when you're doing your hydrant flushing, you can collect samples for solids or particulates to at least determine the loose deposits that are coming out during flushing. That's another approach. You could also be collecting sediments, biofilms, pipe scales to have an idea of accumulation. So really there's a big gap because the way the regulations are set up are not really accounting for the distribution system being a source, first a sink and then a source for contaminant accumulation and then release. So I think we really need to be a bit more proactive than what the regulations currently tell us in order to be able to avoid those problems. In some of the really high arsenic levels that I reported, there were some consumer reports about water being discolored, but that's not always the case. You know, you may have something that looks and smells completely fine and then be loaded with inorganics that can be hazardous. So just the visual observations of a consumer are sometimes they can really pinpoint to a kind of big problem that exists, but not always. And I really encourage everyone to be thinking about the distribution system and ways to kind of figure that out. And not all of the systems will be the same. Some of them will be cleaner. They may not have these issues. They may be belonging in this pattern A, which is great. But it would be nice to know where you belong and then be able to predict any sort of problem you may have.
Yeah, those are great tips. I know, you know, historically, you know, when people would complain of, you know, yellow water or red water, and, you know, I so many times would hear, you know, people say, well, it's just iron, you know, but I think what you're saying is that, you know, well, maybe not, depending on what's out there and what your history and your water contains and things like that. That may not be, you may want to pay attention to that and take a closer look if that becomes an issue. Okay, well, I think I'm going to wrap it up. I think we're right at 1 o'clock. So I really, you know, really appreciate our speakers, and I appreciate everyone tuning in. I think this went really well, and there's still some questions still out here, and I would encourage you to certainly reach out. You know, I think you probably caught everybody's email addresses, and they're in the presentations that are on the page here. So, you know, reach out to them afterwards if you have any additional questions or I didn't get to your question. Again, thanks to everyone, and take care.
Thank you. Bye-bye.
Thank you.